Okay, questions to this point? Sometimes we take notes on the board of myself because those are things that I forget. For example, I forgot to mention that my visual memory, face memory is 0. So if I meet you, etc., you ask, oh, good morning, professor, or good afternoon, whatever, I will answer, I will say, okay, bye, good morning, good afternoon, but I don't recognize you, unfortunately. Because in some cases, I would like to be able to recognize the students at the exam, but my memory is absolutely, for places, absolutely nil. Sometimes I forget to tell you something important in class because I don't like to read notes and copy them on the board. I tell you what is important, but sometimes I miss points. So if you have the notes, the written notes, and you notice that I missed some important point, let me know. Somebody asked me about labs. In the not official labs, that means the voluntary labs that will be during the class, if you want to come, you are very welcome. There will be guided experience. You are not left alone, do whatever you want. No, there are guided experience. Next week we will deal, for example, with the first topology of this class that will be the buck converter. The next weeks there will be other topologies, there will be closed loop, etc. Those are all guided. In the lab, you will use board, pre-assembled board with power supplies on it that can be used open loop, closed loop. You will have to design the compensation, and we will see. Because it's very hard to mount a power supply, power circuit, a switch mode circuit on a breadboard and having it work. Probably if you had the class with Professor Sansoe, did you? Mm-hmm. You mounted a buck converter, but it's very critical if you mount with wires, etc. It must be on a PCB with low inductance traces, etc. Mm-hmm. So you will have these pre-mounted boards. You will have to parameterize them, to put components on it to make some effect, some behavior. But it will not be. It won't be a lab. Do whatever you want. It will be guided. We will have the instructions on the website. I will put this week the instructions on the website for all the experiences we will have in the lab. Overall, we can have something like 6 or 7 labs because 3 or 4 open loop experiences, 1 analog designing compensation, and 1 or 2 for the closed loop behavior. So more or less is that. Then you had a very interesting question during the break. Say, okay, we need to use inductors because in order to get high efficiency, if you have switches, we cannot connect 2 capacitors or a capacitor with a voltage source in parallel. We need inductors. And somebody asked me, can we use synthesized inductors using a gyrator or a circuit like this? Answer is no. It's no for a lot of reasons. The least important reason is that in a gyrator, your inductor is synthesized, it's a grounded inductor. It's not a floating inductor. But who cares? It's not that the main reason. The main reason is that a gyrator needs an op-amp. And we use op-amp in our circuit. So an op-amp is fine. Because we already use it, an op-amp takes from the power supply, let's say, less than 1 milliamp current, so we can just neglect it. Fact is that in our inductors, in power supply, power converters, switch mode power converters, inductors carry a current of the order of amps, a large current. If you want to synthesize an inductor using a gyrator with an op-amp, you need a power op-amp. An op-amp that is able to deliver from its output amps of current. Exactly the same current goes through the inductor. Is still an inductor? Yes, it is still an inductor, but unfortunately, an op-amp that is able to supply amps on its output has a very bad efficiency. Because the op-amp usually have a linear amplifier in it, so this op-amp will just give you all the losses that you try to avoid. So no way to use synthesized inductors. You can use synthesized inductors in filters. Filters are okay because filters are small signal. The current flowing through filters is very minuscule. It's microamps, milliamps maximum. So who cares? An op-amp is fine. But in a power supply, all our components will carry currents that are very high, can be very high. And one part of this class will be about stresses for components. When you design inductor, I don't need just the inductance value. I need the inductance value, I need the current flowing through it, I need the peak current, the RMS current, etc. We will see stress analysis. So, nice try, but not working. And before starting with the real stuff of this class, let's just do a small basic for what will be the subject, the main subject of this class. In this class, we have three main subjects, and we expect the questions on all of them. First subject will be basic topologies of power mode converters. Topologies like buck, boost, stuff like this. We will go quite in details for these topologies, and we will learn how to design them in a real way. That means not just giving, for example, the capacitance value of the capacitor voltage, but also the stresses, the current stresses of the capacitor, how to choose an MOS transistor, how to choose a switch, how to choose an inductor, etc. The second big subject, that will be our core business, this class will be model, small signal model. Of these topologies. Why do we need a small signal model? Because I want to close a loop around these topologies, around this circuit, in order to control the output voltage. If you want to close a loop, you want to have a feedback to control an output voltage, an output quantity, you need to know what is the transfer function of the object you want to control. Otherwise, you cannot design the control around the loop, the feedback loop. And there will be a nice story about this small signal model. It's quite a recent, relatively recent stuff. The last subject of this class will be the derived topologies, derived converters. That means converters are based on the basic topologies, but they have an extra transformer to make them isolated, to make them the real power supplies you have in your life. So there will be the three main subjects: basic topology, modeling, and derived topology, isolated topology. Topology that you can connect from one side to the main and the other side to don't get hit by the electricity. Your written exam, the design part, will be about a derived converter. I will give you the specs of a converter, and the last requirement will be isolated. This converter has to be isolated. So you will need to design a derived converter. We will see around the end of this class. Somebody forgot to remind me about homeworks. Who is that guy? Okay. You will have 3 points less on your final exam because you forgot to remind me about this. Situation is like this. On the class description, there is written that for small classes we can have homeworks substituting the written exam and, I can tell you the truth, the oral exam. That means you make homeworks during the semester, and your final exam will be just a discussion going through the homeworks. What did you do this, etc. Unfortunately, this cannot be done with with the numbers of this class, because 40 people, I cannot grade 40 homeworks every week. And I don't want to have somebody making homework, somebody going for the standard class, because it's just a mess. So, no homework, so the exam will be with the rules I gave you at the beginning of this class. But he is the guilty guy, told me, homeworks, even if they don't give us any formal increase in points or in grade for the final exam, could be helpful, because we start to see more problems, more or less the same kind of problems we will have for the final exam. We are forced to study and to understand week by week. So, if you are interested, I could give you homeworks basically every week, but not every single week, probably we'll miss a few weeks, of designs that can be just initial design of something that is similar to what you will find on the final exam. We will start, for example, we could start, for example, designing some basic topologies. Those are not the problems we will have or we will find, but designing a basic topology is basically a big part of what you will have to do on your final design. That means you have the same kind of calculations to do. In some cases, the derived topology is just a basic topology plus one component. And so, if you learn to design a basic topology, your life designing a derived topology will be quite easy. When we go to small signal model, and if I give you a homework to design a small signal, to find a small signal model, that will be exactly what you will have to do for the derived topology. If I ask you to design a compensator for your system, it will be exactly what you will have here at the end. So, if you are interested on the voluntary basis, it's not required, does not give you any formal advantage, I can give you every week homeworks, that means design problems, to just get trained for the final exam. Does it sound okay for you? Or you say, who cares? They are not required. I mean, if you don't solve your homeworks, who cares? It's not a big deal. But I will give you on the website every week a few homeworks saying, try to do this or that. In some cases, I will give you examples of design. You are designing these basic topologies, especially Bock and Boost. And we could use, as here in class, as a design example, the same problem I give you as a homework. So, when you come over here, you already solved the problem. You already tried to solve it. We will discuss together what's going on. When the homeworks were basically the exam for the class, I was so nasty and so mean that I gave to students different problems for each student, based on the Chinese reminder theorem, applied to the ID number. You have a numero di matricola, an ID number, student number, and based on the student number you got the parameters, the values to put on your system, and Chinese reminder theorem guarantees that you can have all different problems. I don't do this because this is not important. If you want to work together, please do it, because working together is a good way to understand, to get to the point that you would have missed during the lecture. So, if you are interested, I can try to put online a few homeworks and see what happens. This is my scratch pad, where I take notes for things that I forget. You know what is an absent-minded professor? Well, it's me. So I forget things. Previous experiences. What previous experiences did you have on power electronics? Is somebody of you never had any experience on power electronics from the previous classes? You already know what a buck converter is? Yes. Yes. You do? Yeah. Somebody, buck converter is, buck in English means also money. Dollars or pounds or whatever. Buck converter is not a box where you put your money and you get some other money from it. It's differently in this case. So, the beginning, the first lecture will be basically refresh on the basic topology, buck boost, choke, whatever it is. We will go into the details because I want to find out what are the stresses of all components, what are the design criteria for all components, but basically will be standard stuff. What is new, probably for you, will be the small signals model and the derived computations. The beginning is soft stuff. Okay, we have did somebody have a class of power electronics in the bachelor class in the triennale? No? Somebody coming from different university. Here in the Polytechnic of Torino, there is no power electronics for bachelor classes, in the bachelor triennale now. But in other universities in Italy and abroad, there can be a power electronics class in the triennale, the first 3 years of the degree. Did anybody have a class in power electronics in the bachelor undergrad? No? Okay. Before going into the topologies, let's talk about families of power supply, so switch mode converters. And remember, my focus is basically on DC to DC converters, but this is quite general, can be applied for basically almost all converters. The idea is that we have different families of power converters, and these families are distinguished from by the waveforms that are inside the converters, voltage and current waveforms. And basically, we will just study one of these. The idea, when you have the first idea of a converter, then you can easily extend it to the converters. And the first family is the square wave converters. And guess what? As the name tells you, the waveforms in these converters are basically square waves or trapezoidal waves. You can have a square wave converter that has a voltage like this, or a current that is like this, something made of straight lines, straight segment. Then you have a quasi-square wave, and square wave is also called resonant transition. It's basically square wave converter that has square waves voltage in it, but the transition, instead of being steep edges, are resonant, are part of a sinusoid. So you can have something like this. You have just smooth edges. This is an advantage for electromagnetic compatibility, because the smooth edges make less electromagnetic noise. They have a smaller spectrum, a narrower spectrum than square wave. Then you have quasi-resonant converters, and quasi-resonant converters are converters having part resonant and part straight wave. It's not just the edge that is resonant and then you have a straight wave. You can have something like that. Large part of the transition can be resonant and then you can have a straight line. Resonant converters voltages or currents are basically sinusoidal, or part of the sinusoidal wave. You can have, for example, something like this. There are no converters having this waveform. It's just to show you what the quasi-resonant converter is. It's not a sinusoidal periodic forever. Could be you can have a part of sinusoidal to this point, then you start another sinusoidal like this, then you start another sinusoidal like this. Those are not exponential. Those are arcs of a sinusoidal waveform. because you have an LC resonating, and when the switch opens or closes, the circuit changes and your behavior can change. And the end, it's not used anymore so much, it's the multi-resonant converter. And the multi-resonant converter means it's still a resonant converter, but is part of sinusoidal waveform are not at the same frequency. They change frequency because when a switch opens or closes, adds or removes the capacitor from the circuit, and so that frequency changes. But those are not, well, those are important in some very narrow cases. We will stay basically on square wave converters. Those are the most used around the world. With the resonant converter, you can get better performances in some cases, but they are harder to design. In some cases, you believe, you hope to get better performance, you don't. We will stay with square wave converters. I can tell you something about quasi square wave or resonant, but we want to design those converters. If you have the basic ideas about the basic topology, the basic ideas about the switch mode power converters, you can easily understand and learn all the different topologies that you don't see in this class. And in 60 hours, you can do so much. Okay, let's go. Square wave converters. That means our switch is open and closed. We have no resonances in the system, and we will use for the beginning 4 assumptions, 4 hypotheses. And our 4 hypotheses, that's just a way to make our life easier, to simplify our analysis, are those. We will consider, when we analyze this circuit, we will remove these limitations, but just let's start with in an easy way. If you don't want them, you can just remove them at the beginning, but I guarantee it's more difficult. We will consider our switches are ideal. An ideal switch is something that is either open and with when it is open, there is no zero current flowing through it, and real switches are quite close to an ideal switch. I mean, an open switch has a very small leakage current. It can be neglected almost always. And when it's closed, there is no voltage across it. V equals 0 across a closed switch. This is not so true. When a switch is closed, there is some voltage drop across it. If it is saturated bipolar transistor, it could be 1 volt. If it is an IGBT, it could be a couple of volts. If it is an MOS transistor, well, we can choose an MOS transistor to have a very small voltage drop, but there is some voltage drop. We have to consider it. We will consider later on. By now, ideal switches. If you want to add a real switch, that means we add a voltage drop across the closed switch, we can do it, it's very easy. But the very first analysis will be without losses, ideal switches. Second point we'll consider is the RC or L over R time constant let's call that tau. Those constants, tau, are far larger, quite longer and longer, quite longer than the period of switching. That means the period of time where our switching stays closed or open. What does it mean? It means that in my circuit there are capacitors, I put that. There are inductors, I put that. There are resistors. Where are they? Well, the load can be represented as a resistor. The load is what takes the power, so it is a resistor. But in this case, this RC the load resistance times the capacitance has a time constant that is quite longer, far longer than the switching frequency. So we will have that if you have an RC circuit or an LR circuit, you should see exponential waveforms. Well, we want to deal with exponential waveforms. We will deal with linear, straight waveform. That means linear, straight waveforms. No exponentials, even if the real waveform is an exponential. If you look at to an exponential only at the very beginning part, it's static. It's like e to the x, e to the power of x is 1 plus x, and then you drop all the other terms and you have a straight line. Not only, but this R could be also the parasitic resistance of an inductor. An inductor is made of wire, electric wire, copper wire. And a wire has a resistance. So each inductor, it's a real inductor unless it's a superconducting inductor, has a resistance. The magnetic core inside an inductor generates losses, has losses, and so it looks like a resistance. Well, we will consider that these resistances give you a time constant that is far longer than this width. Our waveforms are linear, no exponentials. If we have an L and a C, what do an L and a C together? Resonant. They give you a sinusoidal waveform. But if you look at the sinusoidal waveform, just for a very short period of time, your sinusoidal is a straight line. That makes our equation far easier. And an effect of this assumption is that efficiency of these two assumptions, both of them, efficiencies is equal 1. Is it possible? No way. But at the very beginning we will use this assumption. We will remove it. By your final exam you will have to consider losses and to give me an estimate, not a calculation, just an estimate of the efficiency of your system. You will have to find out how much is the power lost on the transistor, on the diodes, etc., and give me an estimate of your losses. But for the beginning, that will be what we do. Then, third assumption, we will cheat, basically, because we will consider, in some cases, that the output voltage of a power converter is constant. That means no ripple. The output voltage, the real output voltage of any converter is something like this. This is time, this is voltage, and the output voltage will be something like this, for example. I exaggerate the ripple, otherwise you might say. Well, we will consider, we will make our analysis, we will analyze our circuits considering constant output voltage. Then we will say, okay, the output voltage is not constant. We'll find out how much is this ripple voltage, because this is important. But we won't consider this ripple during the analysis. This output ripple will just pop up at the end of our calculation when we say, okay, this is our converter. How much is the actual real output voltage, output ripple from our converter? Actually, it will be a little bit more involved in the system, but that's it. Those are the basic three assumptions. High efficiency, ideal output. Then, at the beginning, we will remove this very soon, but at the beginning we will add a fourth hypothesis. That is, if I were in the electronic circuit class, I would say steady state analysis, DC analysis. There is no steady state in a switch mode converter, because the switch mode converter, your switch opens and closes continuously, periodically. So there is a sort of steady state that is not freezing the switch in one position. That is called cyclostationary condition, We will make at the beginning a cyclostationary analysis. It means that each cycle is equal to the previous one. All the cycles repeat exactly with the same shape, same values, etc. Is the equivalent of the DC bias point for a linear circuit. We will remove this. When we get the small signal system, we will just say, okay, it's not cyclostationary anymore. We can change the parameters and see what happens at the output. Okay? Those are our guidelines. By the end of the class, we will remove these. By the end of the class, we don't remove these. We won't remove these because there is a very small effect. Efficiency won't be 1 anymore. We will find out ripple, the output ripple. Actually, we don't find out the output ripple. We will design our converter to give us a given output ripple, no more than, and then we'll give you the specs. And then, at the beginning, we'll use a cyclostationary condition, that means all cycles are the same, and then we'll remove it this way. If we go to the basic topologies of power converters, DC to DC converters, we have basically two basic topologies. And the two basic topologies we have, if I tell you something that you don't know, please stop me, because I assume that from the previous classes you know already what I am telling you now, at least the names, at least the words. We have Buck topology. In a Buck topology, the important property of a buck converter is that the output voltage divided by the input voltage is less than 1. Or, if you want to read it in an easier way, you can say that the output voltage is less than the input voltage. If you want to be a normal engineer, tell me output voltage in a buck converter is smaller than the input voltage. It's okay. The phrase that I just told you is absolutely right. If you write this like this, well, I can take an issue about it. Because if the input voltage is 10 volts, the output voltage can be 5 volts. But written like this, if the input voltage is negative 10 volts, what is a number that is lower, smaller than negative 10 volts? Will be negative. Give me a number.
So the answer.
No, a boost, a buck converter cannot have 10 volts negative sign at the input and give you 15 volts negative sign at the output. But this is what this expression tells you. I can't put magnitude signs or actual values because the system just becomes more complicated. This is the right expression. Input and output have the same sign, and the output in actual value is smaller than the input, but has the same sign. If you want to tell me this. If you want to tell me or write to me output voltage is smaller than the input voltage, same sign, is absolutely perfect. Then there is another converter, another topology that is called boost, where V0 over Vin is larger than 1. Or V0 is larger than Vin, but be careful because how much is a larger voltage than negative 10 volts? Larger voltage than negative 10 volts is, for example, negative 5 volts. That's not the case. But if you know what boost means, the verb to boost means, you know what this means. Usually we are used to think in terms of positive voltage. Our ground, our reference voltage is 0, and our voltage is positive. Be careful if sometimes we need negative voltage. These two topologies are not unrelated. One is the dual topology of the output. There is a duality of these two circuits. We will see this duality later on. Then there are two more circuits, and then the blackboard is finished. What other topology in basic DC to DC converters do we know? Buck boost or flyback. This is interesting story. Another one is a buck-boost converter, and the buck-boost converter, I call it buck-boost. The buck-boost converter, long time ago, was called the flyback. Oh, by the way, buck-boost have also different names. I use usually buck-boost and buck-boost, but buck-converter, being a converter that has an output voltage smaller than the input voltage, is also called a step-down. And the electronic guys call it step-down. Boost converter, having an output voltage that is larger than the input voltage, with a very big struggle of fantasy, can be called step-up. Buck-boost converter, buck converter from the electrical engineer, not electronics engineer, from those who use buck converters to drive the motors, they don't call it buck or step down. They preferably call it chopper. So buck can also be called step up. Step down can also be called a chopper. If you hear the name chopper for this circuit, it means it's somebody going to electric machine, working with motors, etc. It's not an electronic design, it's an electrical design. That's okay. To chop is the verb to slice things with a big axe. Chop, 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 chop. But boost, as the name implies, is a buck and a boost combined together. And the characteristic of a buck boost is that V0 over V in, the ratio of these two voltages, is less than 0. This is, V0 is opposite sign, opposite polarity of V in. You enter with the input voltage, you get you enter with a positive voltage, you get a negative voltage at the out. This buck boost was, in the very long past time, was called flyback, because step up, step down, and flyback, or inverting circuit, because it inverts the polarity, were considered to be three different topologies, three unrelated topologies. When I learned the first time this stuff, they told me, oh look, there are only three topologies because you make a permutation of a diode, switch, and inductor, and you get the three topologies that were step up, step down, inverting, or buck, boost, and flyback. In the, I think, 70s, not so sure about the year, but it should be in the 70s, there was a guy who started to work on buck boost, looking at buck boost, and realized that actually it was flyback. At that time it was called flyback. He realized that the flyback is just a buck plus a boost melted together, placed together. And from that time the name flyback started to drop of use for this circuit. Flyback is still used for a different circuit, and it was called buck boost. So if you discover that the circuit that was considered as an independent circuit actually is just a buck plus a boost, what is the first idea you have? If you discover that a circuit that was considered an independent circuit from other circuit actually is just a buck plus a boost, and you call it buck boost, what is the idea you can have? Exchange them, swap them. Let's try to invent it. If you swap them, what do you get? The boost buck. Sure. So, the fourth topology is a boost buck that has the very same characteristic of the buck boost. The V0 over V in is less than 0. Oh, what does it mean? V0 over V in is less than 0. It means that V0 and V in have opposite sign. it does not, V naught can be magnitude-wise smaller than the input or larger than the input. You can go in with 10 volts, positive 10 volts, you can get at the output negative 5 volts, or you can get at the output negative 20 volts. It's quite flexible. Well, the story didn't go exactly like this, because the boost box exists. It was used, it's still used for a given time, but it's not called boost box, because the guy who invented, who discovered that the flyback is just a buck boost and invented the boost box, called it with its name. And the boost box actually is called Chuk. Chuk is a Serbian guy who worked in the Caltech, had his PhD at Caltech, and he discovered that stuff and invented the Chuk converter. And for the people speaking the local language in Torino, Chuk means drunk. But Chuk has also another meaning, fortunately. Owl. A Chuk is an owl. You know what an owl is? Owl. And when I told to Mr. Chuk that his name in my mother tongue means either drunk or owl, he was very happy, was laughing, saying, but remember, owl is a sign of wisdom. So you are a wise guy. A wise person. Anyway, Chuk is a boost box, and being this guy in the United States, he said, okay, I invented something, I patented it, and I make money. And Chuk patent is a converter. He started a company manufacturing Chuk converters. They were good converters. Unfortunately, Chuk converters were at that time, and still now, quite difficult to design. They have some quirks that make them not so easy to design. And Chuk required, if you wanted to manufacture a Chuk and sell it, you had obviously to pay royalties, but he wanted to have your design made to him and the prototype made to him, so he was able to check it. And I asked him, why? And it's easy, because a Chuk converter is not easy to design. People is not used to design it. There are no books explaining how to design a Chuk converter. I don't want that somebody tries to design a Chuk converter, makes some mistake, gets a bad result, and say, oh no, Chuk converter is a crap converter. Chuk converter is a good converter if you know how to design it. And so he went just through all the designs of Chuk converters in the world, or almost, to check that everything was okay, so that his name was not spoiled by some bad designers. Then the Chuk patent just expired a few years ago, so you don't have to pay royalties anymore. But it's still a converter that is not very easy to design, because there is no tradition of designing Chuk converter. Chuk converter has good properties, we will see that. But you don't find it in any textbook. And so designing it is not sort of trivial. And then Chuk company, actually Mr. Chuk got divorced, and he had to sell, to close his company, to sell the company, to pay damages to the wife, etc. So now the Chuk company is closed down, it's not working anymore, even because Chuk wants to retire. Actually, he's retired. Has retired a few years ago. Chuk was a professor at Caltech, and when he started his company and he saw that his company was going on, he just resigned from Caltech position and worked full time in this company, because he told me, I make more money with my company than not teaching at the museum. Anyway, those are the four topologies: block, boost, dual. One is the dual of the other one. And the characteristics of this output voltage is larger than input, is smaller than input voltage, output voltage is larger than input voltage, same sign. Buck boost and Chuk converter, output voltage is opposite sign than the input voltage, can be the magnitude larger or smaller. It's quite flexible. And now we will go to buck boost and buck boost quite into the details, and we will see basically briefly the buck boost to converter. In my career in power electronics, I think I designed only 2 or 3 chip converters because nobody wants it. It's a good converter, but nobody wants it, and in some cases it's good to design a couple of them. Not so much. It's not so common. Okay, buck converter. Step down. Chop. Buck converter, schematic of buck converter is something like this. We have an input voltage. I will take, and in many cases I forget to put the signs of the input polarity. I will take the positive polarity on top. And the buck converter is something like this, at least in its standard form. There is an input capacitor, say ping, a switch, S, a diode, D, an inductor. You know this schematics, don't you? Yes. Even it is a light second. An inductor, L, an output capacitor, C, not, and here, that is a sine converter, there is our load resistance. Oh, we don't put a resistance at the output of a buck converter, a heavy converter, most of the time. We put our load. But I don't know what the load is. I am interested to design this part. The load can be any load. It can be a computer, can be anything you want. So for me, the load will be just a resistance. This is the basic topology, the basic schematic of a buck converter. This switch can be MOS transistor, IGBT, BJT, thyristor. Do you know how a thyristor works? It's a SCR, silicon controlled rectifier. Thyristor. Everybody knows about thyristors? Yeah? Say no if you don't. Thyristor is a diode that is turned on, switched on by a command in the gate, but it switches off only when the current through it goes to 0. You command the input, the turn on, but the turn off is given by the circuit. When the current goes to 0, it turns on naturally. You cannot turn it off. It's not like a transistor, you can switch it on or off whenever you want. Well, if you have here a thyristor, you can switch it on. There is no way to switch it off. So, not a good idea. There are thyristors used in buck converters, but the buck converters are far more complicated because they need to have an auxiliary circuit to switch it off. They were used on the old locomotives, electrical locomotives, the first one that had the electronic on it. They had a buck converter type circuit with a thyristor, because the thyristor was the only power electronic switch, and an extra circuit to switch it off. This is a switch. What about the diode? Diode is diode. Is a diode a switch as well? Yes, no. Yes, dependent. That you are for yes, definitely. And then there were another one was said, yeah, might be more or less, who knows. Somebody's for a no. No, it's not a no. It's not a switch.
Not complete. There is a voltage drop on the...
Oh, even on an IGBT there is a voltage drop across it. It's not an ideal switch, but is it a switch?
It is work as a switch.
In this case it works as a switch, yes. Who cares if it is a switch or not, as long as we are today in this class. But I saw a very interesting trial on a patent infringement accusation about the fact that somebody wrote down a patent saying, calling this diode a diode. Another one changed the circuit, placing instead of diode a transistor. And so he claimed that the transistor was not a diode. And he won the case because if you put here a transistor and you patent here there is a diode, a transistor is not a diode. If you patent this is a switch, you cannot substitute this with any other switch because it's still a patent infringement. So, in some cases, engineers don't pay too much attention to words, say, okay, it's a switch to diode, who cares? No. If you go to the lawyer for patent infringement cases, this is important. Is it a switch or not? Yes, it is a switch. Because it opens, it closes. It's not controlled by you, it's controlled by the circuit, but it still opens and closes, so you can legally consider it a switch. When you have lawyers going around, it's always fun or painful. Fun if you are not involved.